So it's a pleasure. It's a pleasure to present Erhan Öztop as part of ROMER Talks. He's joining us from Osaka, right, at the moment,
Yes.
and he graduated from computer engineering, and as a matter of fact, when I left for my PhD in US, I left my office to Erhan, so he's my successor in that sense. He had earned his PhD from University of Southern California in 2002. In the same year, he joined the computational neuroscience laboratories at ATR in Japan. There he worked as a researcher and later as a senior research and group leader, where he also served as vice department head for two research groups. In 2011, he joined Özyeğin University in Istanbul as a computer science faculty member. Currently, he is a professor at the Department of Özyeğin and also a specially appointed professor in Osaka University at the Symbiotic Intelligent Systems Research Center, Institute for Open and Transdisciplinary Research Initiatives. His research interests involve computation modeling and analysis of intelligent behavior, human-in-the-loop robotic systems, machine learning, cognitive and developmental robotics, and computational neuroscience. Without further ado, I'd like to leave the stage to Erhan. As I said, we have a whole class here, plus the online, basically online listeners.
Great.
We're talking about resource economy in cognitive modeling.
Okay. Thank you very much for your kind introduction, Errol. I'm very happy to be here. I would like to be there next time physically. So let's go. I hope this talk is a little bit multidisciplinary, a little bit talks about biology. I think we'll find something useful in some places of the talk. But let's go, basically, okay, if I can. Yeah, so the question is actually that bothers me is how is the brain wired, right? I mean, we were evolved from some low-level creatures. So how is the brain wired? So basic thinking is evolution must have optimized our brains for ecological fitness, which means that we have to survive with less energy and reproduce, right? So this means that for the brain must do optimal wiring, neural packing, optimal signaling rate and codes. Okay, and we have to consider, not we, but the evolution have to consider wiring cost and topological value of brain networks and so on. And these are very much studied from this different fields based on neuroscience and its evolution. Another topic which is very much I like is neural exaptation and neural reuse. Neural reuse means that you have a circuit in your brain, and after some many centuries, it becomes to be used for something else. Okay, but it keeps its own purpose. And if you look at the neural exaptation, it is similarly, but it is told that the original function get lost. Okay, these kind of things happen during evolution, and based on this, can we input something from these ideas into our computational modeling? Okay, so in particular, I want to say, if we have this kind of optimization working, and what is the effect of this on behavior? Okay, so the first thing you can see, for example, we have no luxury to compute till the end. So, for example, when you see, if you're a man, if you say woman, and you want to decide whether this is the best woman for your life, and if you start computing, your life will end, right? So you have to decide in a fast way. So you can say this is the reason of love, right? Or emotion, for example. So, I mean, I try to find some basis of this kind of behaviors in this neural optimization, basically. Okay, you can have, for example, we have fields called intrinsic motivation that drives you to do things. One intrinsic motivation must be relying on this low energy use, right? So this can be explaining why we want to be lazy. Okay, computational basis of laziness, for example, could be a nice PhD topic. Okay, so these are the general framework and things I'm interested in. So what I want to now go in is give some examples of some computational models where we can see some of this neural reuse ideas. Okay, so the first thing is mental state inference model, which is an quite dated model. Here, we wanted to generalize the grasping circuit, and this is representing a monkey brain, and this region is parietal area. And you have in this area you have neurons that represent object properties that are relevant for manipulation. Okay? And this region is connected with the premotor cortex, where it is believed that some motor planning is taking place. Okay. And if you take this idea to a wider scale, not only grasping, but also any goal-directed action, we can see a control diagram like this. So if you want to reach a goal, a point in space, or if you want to grasp an object, for example, you have to monitor how your hand is related to the object, whether you are far or close, right? So we can believe that there must be some region in the brain encoding this error, how much you are far away from your this goal. Okay, and this goal can be a position in space or can be a orientation and the position if it's a grasping, for example. So, and the most likely candidate is parietal area for that. We imagine that you have this computation happening and you get a signal, and the signal is given to premotor cortex where motor planning takes place. Okay, and this is a higher level area, motor cortex, and here you can get lower level motor signals. You can imagine that this could be like maybe desired joint angle changes. You can imagine robotics. And then you have a lower level controller which runs this dynamic loops. Okay, so this is taking care of primary motor cortex and spinal cord and in general central nervous system. Okay, so eventually your signal from the premotor cortex leads to a change in space. So you see what happens. You slowly approach your target, for example. Okay, then you can compute a new error, and this goes on like this. If you're a control engineer, you know that this is a simple control diagram. This should happen. So we try to map this to the human brain in some sense. Okay. So this is all good, but of course, this happens in the brain, and we don't have only single task. So you have to switch which task you want to do, right? So we can consider that prefrontal cortex, the area in the frontal part of the head, is actually the part that makes us human. And this part have our voluntary wishes represented and instructed to the lower brain areas. Okay, that's how usually it is believed. And we can imagine that this area switches the schemas necessary for a given task. For example, if you are hungry, then you want to basically set your goal as a shop next to you, like pizza restaurant, for example, and your task will be now the walking there. Okay, so you have multiple circuits, and this mental state selection, intention and goal selection, basically selects which circuit to be used at that time. And that is a basic structure of the human brain, if you will. Okay, so now this is all good, but one problem with this control structure is there's a huge delay in the system, right? I mean, you have vision coming in, for example, and then you generate some signals, and there's a neural delays between the areas in the brain. And then you send some motor command and lots of steps, maybe 5, 6 different layers, regions are passed. And then the movement happens. And this loop has at least 300, 400 millisecond delay. So it's very difficult to move fast if you have this kind of delays in your system. So what people believe that is you develop a forward model so that you can compensate for your delays. Okay. And initially maybe we are moving fast, but moving slow. But later, when we have this internal model, we can compensate for delays so that we can move fast. Okay, so that is many people believe that happening in the brain, and there's many neuroscientific works showing that forward model exists. So why I came to here, I want to bring this circuit, everything is now in motor control. Everything is based on movement. So now here we will make a case for reuse. How this can be done is like this. If you can inhibit your movement execution, okay, and then you have actually a system here where you can make a movement simulation. You can imagine a mental state, say that, you know, there is a cup here and I want to reach for it. And then you can just say what I would do if I want to move it there. Okay, of course, this is running in a much lower time scale, smaller time scale, but you can imagine how things will move on. Okay. And of course, you don't generate pictures of what's happening in this case. You are predicting the signals that would happen in real life. I mean, these are the signals that your parietal cortex will be giving to you. Okay, so in a way, you have this. You can imagine some. If of course depends on the quality of your forward model. If it's a good one, you will generate really nice predictions. But of course, you cannot do very far prediction. But let's believe that this works there. And what you can do now is, interestingly, the rest part of the circuit is kind of idle, right? Especially the parietal cortex is actually now not processing any visual input, but actually it can, right? So you can make it watch some other person, for example. Okay, so you can say, I'm now watching someone else reaching in space, doing some movement. And I could ask my parietal cortex to compute these variables that it was computing for me before, like distance between a goal and the hand. Now it's computing that for another person, another hand, and another imagined goal. Okay. So this way, actually, I can generate two streams of information. One is from mental simulation, and the other one is from the signals I collect by observing someone else. Okay. And then if you just compare these streams of signals, you can actually try to estimate what the other guy is doing. Okay, so I call it here mental state inference loop. So if you know there's four possibilities, it's very easy. You can have four possibilities. He can grasp apple or drink coffee or something like this. And then you can try four of these options and see which one is most likely. Okay, so that is the idea basically. And it is a very old idea, as you can see, 20 years ago almost. But here, what is interesting is we used a circuit that was developed for self-control movement for perception, basically. And just to show if it works, now here, basically, we have two agents. They have the same motor system, and the observer here also uses this mental state inference loop to estimate where would be the goal of the actor. Okay, so the thing is, the motor part is the same, and we are running this mental state inference loop, and it can predict where the agent, the left agent goes. Of course, it's a very simple task, and we showed more complex tasks can be also estimated like that. And furthermore, we showed that the left actor can actually try to deceive the observer by making a fake movement, for example. Okay, but for the sake of time, let me show you another idea similar to this. Grasping a tool actually tells us what's our intention on to do with the tool. Okay, if you are, for example, gonna grasp the tool, if you are gonna use the hammer for driving a nail, you should grasp the tool like that, the hammer. But if you are gonna pry off a nail, you should just use the opposite grasping, right? I mean, you know that when you want to pour some coffee in your mug and the mug is upside down, the way you grasp it is just this awkward movement like this, and then you just do it like that, right? So anyway, so this initial portion of your movement tells you what you will do afterwards, and this is a known fact from human behavioral data. So with this idea, basically, you could just program the agent to grasp, and by using this computing the variables of the orientation difference between the handle and this hand vector, and also controlling the distance. Okay, two things at this, two parameters is computed. Okay, and with these two parameters, you can make a feedback controller like that. And now with two parameters, the observer can try to understand what you are doing. As I suggested previously, the observer can hypothesize that you are holding or you are driving a nail or you are prying off a nail, and then make a comparison between these two series of two streams of signals and guess what you are doing in the beginning of the, at least until the midpoint of the action. Okay, so that was a maybe the one of the cute ideas that showed the neural reuse may lead to this kind of shortcut solutions for the brain. Okay, but the key thing here is, of course, we have to note that this is possible only when object-centered control is employed, which means that the parietal cortex is programmed to compute, let's say, the distance between a hand and the target. Okay, so this is irrespective of my hand or someone else's hand. Okay, and also you need, of course, action inhibition, because if you are running your motor system, you have to inhibit action, otherwise your body will be moving all the time. And the third one is you need to build a forward prediction system. Okay, but there are sufficient data in the brain suggesting that all of these three mechanisms exist. Okay, and with this model, what we can say, well, you can do basic imitation. Okay, you can understand the goal of the other person and then generate that action yourself. Or you could do deception. I didn't show in this talk, but it's possible. And it can explain mirror neurons in some sense. And now, of course, maybe some of you know about mirror neurons, some of you don't know about them. These are also quite used to be famous, let's say, and they were discovered exactly in this premotor area of the ventral promotor area of the monkeys. And this region is known to be, before that, known to be only motor area. But these guys in Italy, Rizzolatti and his group, discovered that these neurons also respond to pure observation of actions. Okay, so here's a textbook example. The experimenter is grasping a peanut, and the neuron activity is very high. Okay, so you can see here each row represents an experimental trial, and if you average them or sum them, you get this profile. The neuron shows high activity when the monkey is seeing an action executed by the experimenter. Okay, and interestingly, this tray or the cardboard is brought to the robot, and you can, not the robot, sorry, to the monkey, and the activity of the neuron goes down. Okay, he knows that he's gonna eat it, but it goes down. But then he grasps himself to eat. Then during grasping again, the activity increases a lot. Okay, so this means that this neuron encodes vision of grasping and motor act of grasping together. So that was a very big excitement at that time, and there have been many models of this one. So this model I mentioned can lead to this kind of neural behavior or a property, let's say. Why? Because one possibility is that this is the feedback signal we are computing, right? I mean, if as soon as I see an action, unconsciously I am running my mental simulation, or sorry, if I'm running my parietal cortex to understand what's happening in the other side of the story, I mean, other person is doing, then I could be generating these signals. Okay, so when I'm observing, I'm always observing with the unconsciously, with the hope that, you know, I will understand what the other guy is doing or something like that. Okay, so this signal will be generated. But also when I'm executing, since this control loop is running, I'm computing myself this signal. So in this case, you can have this same signal can be generated when I'm executing my own action or when I'm observing someone else. The second place where mirror neurons can be located is the forward model part, because if you assume that when you see a person, a movement, unconsciously we are doing this mental state estimation, okay? We could be generating this forward model simulations in our mind, but of course unconsciously. And this signal could be happening due to mental simulation for when we are observing. And when we are executing, we have this signal just because we have this delay compensation, okay? Because the mirror neurons get activated even the monkey doesn't see its own hand, okay? So it's not purely visual response in that sense. So this may explain these two things also. And we'll come to more concrete mirror neuron system modeling in a minute. So to just wrap up, I mean, there have been lots of mirror neuron system modeling, and actually I did one in my thesis, a PhD thesis, long time ago, and there were so many models afterwards, but all of them focused on learning, okay? And the important thing was self-observation. So you generate actions, you learn how to act, and then you see how the action looks like, and somehow based on that, you are able to generalize this observation of an action and mapping to an action code from other agents of the actions as well. Okay, but that is not, as I mentioned, it's not trivial because self-observation, you're always seeing yourself from first-person view. Okay, so if you're computing this signals based on this view, it's not clear how it will generalize if I see a person 10 meters away, right? So there must be some uh, either transformation happening, you assume that transformation, or the system somehow has this property. In the previous modeling, this happened because we assumed goal-based control scheme, which means that you represent everything as a relative position or relative orientation of the object, which is the goal of your action. Okay, so that helps because if it's a distance to a goal here, the distance from my hand or your hand, it doesn't matter, it's the same. Okay, so let's go. So actually, mirror neurons could be the result of simple associative learning. So what does this mean? And maybe you heard about Hebbian learning. I mean, if you have two signals happening at the same time in the brain, they can enhance each other. If you make this neural level Hebbian connection strengthening in a macro level, you can imagine this is happening, which means that, you know, I always act, do something, I grasp, and I see my hand, okay? The motor code for grasping is there in my brain. And when I see my hand is moving, also the representation of my hand moving is also in my brain, okay? So these two things are there. Also, I have many sensory feedback coming, the vision, vestibular, somatosensory, and so on. I can assume that this is encapsulated as a single memory and stored. Okay? That's one way you can imagine that we learn to represent the actions, the code, the sound of it, the vision of it in a single item in a memory. Okay, and this will work if this memory is such that if I give one part of the memory and the rest can be completed automatically, then this could lead to mirror neurons. And actually, we have neural architectures that can do that, like old Hopfield networks, which can actually do that. And you can imagine that this complex representation is a huge representation, is a single memory item. And then when you see some action of other, then that partial information is given the Hopfield network, and it can, you know, update this internal dynamics, and it can converge to some motor code which corresponds to that vision. Okay. Also, you can do more recent Boltzmann machines, and more novel improved Hopfield networks can do that. These are all good, and actually we tried these ideas. It works quite fine, but it doesn't consider the efficiency and resource economy idea, because if you want to make memories of these things, huge chunks of items, these are not very let's say beneficial for the brain because it will cost energy. So more recently, people are looking at this architectures, probably have used those autoencoders. Okay, so you can imagine autoencoder that takes all the modalities that I mentioned there, vision, motor, sound, touch, whatever, concatenate and then compress them into a latent representation. Okay, and if you do that, you can imagine that while I have experienced my own action moving and I experience the touch, vision, whatever, and I can build this autoencoder network, and I can store the weights. Then when I see someone else doing action, then I can use my network to encode what I see and then ask it to decode. Okay, of course, when I see only the vision, I have the vision, I will have some missing information here, but I may hope that the representation, latent representation here is kind of rich enough that it will generate a likely reconstruction for all the modalities. Okay, so this is a work done by the group of Demiris, which works to some extent. It's not great, but now I'm going to show a model we worked, which we developed and which works a little bit better than that. But the idea is in a way similar. You have the representation of the multiple modalities compressed into a latent representation. Okay, one thing again here I should say, this again needs to have this representation in a way perspective invariant, right? Because otherwise my vision of some action would be so different if I see another person doing some action maybe 90 degrees away from me, right? So that is another issue which is not very much dealt with in this model, but I will show an interesting result with our model that can answer that little bit. Okay, I think that already I did the recap here. So the main question is then, based on pure self-observation, can we discover perspective invariant features? Okay, so until now, all the modeling assumed we can have this perspective invariance, or we assumed goal-based control definition. But without ignoring any of this assumption, just use end-to-end deep learning, and can we say whether I can learn this perspective invariant features? Can they emerge, for example? Okay, so this probably difficult to believe, but we'll show that there is some hope. Okay, so that is the model we developed actually with Emre Uğur and his students. Emre is Erol's PhD student and my PhD student, thanks to Erol. So we work with conditional neural movement primitives. It's a recent model which can basically store trajectories. Okay, it's a trajectory storage system, let's say, and you can ask the system to generate or recall the stored trajectories by giving some hints. Okay, and we call them like conditioning. Okay? So you could say, for example, well, I want the trajectory after training, of course, you say, I want a trajectory that passes this blue points in this time points, okay? And then system will generate you some latent representation that allow you draw this gray line. In particular, you can say if you are to pass through these blue ones, blue points, then what is your prediction for this red one? Okay, we can say this. And if you a little bit open this, what's it? We have an encoder, okay, and a latent vector representation and decoder. But differently from the previous approaches and differently from the LSTM kind of networks, this latent vector representation compresses time also. Okay, it's a spatial representation. It's like a vector, basically, like 500 unit vector, for example. It compresses the time. It includes the time as well as the data itself. Okay, so we don't need to make a feedback to the system to generate next data. This is the biggest, I think, beneficial part of CNMPs. Okay. Right. So of course we can give also the nice thing about this, we can give very different trajectories, and it will basically build a distribution. The latent representation here actually encodes a distribution of trajectories. Okay, so it gives us also some confidence on its own prediction. So that was already the work of Emre and his group in the Boğaziçi University. Now we collaborated here and said, okay, let's do this model combination, compressing all the models into a nice latent representation in a better way. And here First, we started with individual representations, and here you can see that this guy, I said it can learn trajectories of numbers, but also it can learn really video clips, because each time is a big dimensional vector, right? Each frame could be like 64 by 64, for example. Okay. So if your encoder is made of convolutional neural networks, you can also learn to represent these film strips, and actually you can generate them. Okay. And now we have the joint angles. These are like, as you know, each trajectory is probably, if you have a robot with 7 degrees of freedom, each point in the trajectory is as a seventh dimensional vector. Okay. So this system can learn both of them independently, but we want them to do this. We want them to have a single latent representation which learns the trajectory of both the images and the joint angles. Okay. And we want also, by this latent vector, we want to be able to decode in both the vision, I mean the pixels, and the joint angles. Okay. So, and what we came up with this, we decided to have these two individual latent representations to be mixed in a probabilistic way. Okay, during training, the P is selected uniformly randomly. So the system doesn't know how they will be mixed, but they are mixed, and then the system must be able to decode the image and the joint angle. Okay, training takes a little bit long, but once it is trained, the system works very well. I mean, if you can give your joint angles, it can just give you the image of the robot, and you can give the image, it can give the joint angles very well. Okay, so first we test this. So did I went too far? Okay. Okay, before showing the testing results, this is the data we used. We use first-person view of some actions, grasping and pushing actions. Okay, and with 40 variations. And we always see first person, and then we just learn this information in two channels. One is the vision we see here, and reduced resolution. I think it was 64 by 64, and the joint angles. Okay. So as I said, it works very well because this is how it is designed. If you give an observation, let's say, this is the hint I give you. Please, spit me out the prediction of the video frames. Okay, then it can generate these videos nicely. And also, even though it's given only this image, it can generate all the joint angles very, very nicely. Okay, so this is expected. We are happy this happened. And also, you could try, in this case, we have a grasping action hint here, and then the system can generate how the action will look like, and it will also give the joint angles that will lead to grasping action. Okay, so these are the basic tests. So now this is the most interesting part that makes me excited, basically. Now, to remind you that, again, the training data was like this first person view, but we want to test something very strange. We want to give the system this view. Okay, never saw something like that. Okay, and we can see the response. Okay, so for some cases, you have this kind of prediction. So basically, we give a hint from this ground truth. Okay, the demonstrator is pushing the object to left, and the reconstruction of the network is some action which is not pushing left, it's pushing right according to himself, but object is moving in the absolute sense to the left side. Okay, so this is, we can call this object-based imitation. Or in the grasping case also, it grasp and move up. So basically, if you want to assign a brain to this network, you can say, oh, it understands, okay, I have to grasp the object and make it up. Okay, so that's basically imitating what the object did. Okay, and you can see other examples of this one. So that was the somehow emergently said, okay, the system first time extremely out of distribution data, and it just says, okay, I will do that. Well, in some sense, you can imagine I initially said this system is a memory system. It stored this information and it wants to pick something and, spit out, right? So in this case, it just picks up this kind of action. which is matching in the object movement domain, but we don't know why. Okay, so now if you have different kind of action, now this is the also Errol, this is the answer to your question. This is the single observation we give to the network, only input, and the prediction of the network is on the right here. Okay, now you can see that the execution is matches the action of the demonstrator. I mean, you can imagine that demonstrator is pulling the object to itself, right? Now, the response of the network is also pull the object to myself. So in a way, anatomical imitation. So in the previous case, if it were the previous case, since the object is going up, our robot's prediction should be push up. But somehow, in this case, it decides to do like that. And this happens also in some other examples. Now, the demonstrator is on the left, and you give this information as an input, as a hint, and again, our system responds by pulling the object to itself. Okay, somehow it has a smart enough to understand this movement is pull to yourself. Okay, so of course we didn't stop here. We try to understand why this is happening. We had this egocentric imitation, meaning that anatomical imitation, and now we did something strange. We removed the body from the demonstration. So now we give input to the system only a hand and the object position. Now suddenly the system actually changed the behavior. So a bifurcation happened. Okay, now suddenly the system started to produce an action which basically matches the movement of the object. Okay. So somehow the amount of body seems like important for the network. Now, if you add back the small part of the body, the base, suddenly again the behavior switches back to anatomical imitation. Okay. So what we can say that somehow the network has this property that if there is sufficient body part visible, it is like a mirror-like behavior, egocentric imitation. Okay, I pull. He is pulling to itself, so I will pull to myself, kind of idea. Otherwise, it's just trying to imitate what the object is doing. Okay, so of course I cannot explain this strange behavior, but I want to say, maybe, I mean, the brain's resource economy drive, this compression of this information into latent representation and combination of all the modalities together creates this kind of strange behaviors. Okay, so what I'm foreseeing from this is maybe this kind of behavior can be biased with additional circuit in the brain, so that voluntary imitation, or we could select basically which behavior to do, right? If you say, okay, please imitate the movement of the object, we can do, or please imitate what I do, we can do anatomical imitation. We have this power to do. But maybe what I'm saying is this this compression of the information, multimodal information, creates opportunities for the brain, such that this kind of potentially different abilities emerge, and we can pick them and then use them. Not we, but evolution picks it, and then we use it as humans. Okay. Okay, so that was the mirror neuron story. Now I kind of switch to neural reuse, and it's an explicit attempt to use the neurons in a reinforcement reinforcement learning setting. Here, the task is actually we want to learn a task and then transfer that skill to another task. Okay, so the first task is to be able to reach the green cell by avoiding the obstacles. Okay, the robot doesn't have inverse kinematics or anything. It has to just make small delta x, delta y movements to learn how to reach, basically. Okay. So, and this is a basically deep reinforcement learning. So everything's happening end to end. So we have this image view, and system is basically exploring the ways to reach the green target by avoiding this rectangular shaped obstacle. Okay, so then after some trial, the system learns that it can avoid and reach the green cell. And the moving things are just basically distractors. Okay. Now the question is, we want to have we have this skill now. We want to transfer it to a new task. New task is not completely so new. In this case, the obstacle shape will be changed. It will be an L shape. Okay. So if, of course, in deep learning, this is now very standard, right? I mean, you can get a big already trained network and then train only the last layer, and you can get skill transfer, which works fine, right? For many image recognition tasks, especially. So this is called fine tuning in deep learning. So of course, here our aim is to a little bit think about the brain and say, well, why do you pick all the layers? Maybe to pick some of the subset of the neurons are better for you. Okay, so that will be more economical. That's why we want to do that, right? So for that, we tried the idea of slow changing. There's the idea of maybe some neurons are representing more meaningful things if they have slowly changing outputs. Okay, this is a very controversial idea. I mean, imagine if it is too much changing, it's noise, right? But if it is slowly changing, maybe it has a meaningful representation. This is called slow feature analysis that was introduced by Wiskott and Cesnowski. So we use this idea. We basically, after training the first network, okay, this is the primary network, we applied slow feature analysis, basically decide which neurons to pick, and then use these neurons as part of the second neural network training. Okay, so normal way would be to pick everything. So we have this 512 neurons here. We would just take all of them and reuse them, and that will be again skill transfer, but it will be a little bit wasteful. So now we are saying that pick useful ones and then use them, and things will be better. So that's the idea. And actually, we tried. Let me quickly. You can ignore PCA because we made it as an alternative for SFA. The none means that in the task to start learning from scratch. Okay. In the x-axis, you can see the number of different setups the system is seeing. Basically, roughly corresponds to a number of epochs times some number. Okay. So as you can see that the y-axis means the percentage path covered towards the goal. So it means the higher is better. Okay, so you can see that the specially selected neurons provide the most effective learning. And this was surprising to us because we have the full case, meaning that we use the full layer information from the first network and use them in the second task. That even that one, we thought, that is the best we could do. Actually, it performed worse. So we are not sure exactly why. But selecting, maybe it allows, it got stuck to some smaller local minima. Maybe if we train enough, it would be better, but we stopped here. So we could see that selection of a subset is a smart idea. And now from the new brain point of view, I'm imagining that there must be some mechanism in our brain. If there's a circuit already trained, and now the information there must be selected by some other circuits, some other neurons, like synapses can go there and grow and pick the right neurons, and then have an economical way of reusing the information. But this is very futuristic, so I don't know how this happens in the real brain, but that is how it should happen, I believe. So to understand what kind of representations we picked, we'll quickly look at this representation. It's a little bit complicated, but just very quickly. I mean, this represents the relative position of the hand to the goal. You change the goal, and the goal is there, and you change the relative hand position, and then you record what the neurons output. Okay, this is exactly what the neurophysiologists do, and by this way you can find each neuron active for something. Okay, so we can see that, for example, this neuron seems that it's firing maximally when the hand is at the goal, and this neuron is firing quite high when the hand is in the right side of the goal, or something like that. So we have some kind of abstract or meaningful representations for a few neurons, but not whole a lot. So I will not go in here too much. So what this says basically, well, there must be some mechanism to pick less number of units that will allow you to save energy, your also time, because you will learn faster, and also you will use less tissue, okay? Because you have to build less synapses. So in this case, we use slow feature analysis, but we don't know what the brain uses for that, but that's a future work. Okay, so one final research topic I'm working on right now. This is also in the topic of multitask learning. Okay, so assume that you want to learn many things, and then how do you choose which task to learn first? Okay, so this is not very well addressed. And usually there is some multitasking learning and continual learning ideas, but you want to have basically choose a task, learn it a little bit, and then form some information and such that that information can be reused later. So that is the dream of what we want to have in this multitask learning. Okay. Of course, right now people don't think about the neural cost, but I think the way we choose tasks must be something to do with also the neural cost. Okay, how much energy we are spending to learn something. Okay. So I think this is a nice contrast between how machine learns and how the humans learn. So even in multitask learning, in state of the art machine learning, we have multiple tasks and they are learned to the completion. Okay, and there is no really task selection and there is no interleaved learning at all, because this is known to cause some problems. Okay, so it causes catastrophic forgetting, and learning doesn't become stabilized. But as humans, we can actually do that, and actually we can benefit from that. So now, within this research framework, what I aim is to show that actually interleaved learning may be useful if you couple it with some task selection criteria. Okay. Sorry, I'm going too fast. Let's skip this one. So the current model, last year we developed something like this. We have an architecture on the left, which can, for each task, there's a single neural network that learns the task, but also they can transfer knowledge to each other, okay, through basically their lateral connections between these neural networks. And that's one thing here. And the second one, we propose a learning progress-based task selection. Okay, so we have a task controller at top. So decide, okay, I want to learn a little bit maths today. I want to learn a little bit physics. I want to learn a little bit, I don't know, history today. And then this is somehow done such that overall learning is improved, meaning that a lot of skill transfer happens, and eventually total learning of all the tasks is improved. Okay, so there must be some optimal task selection scheme. We don't know how to find optimal, but maybe brain is employing a heuristic. Okay, so in this task, in this study, we just checked learning progress. So basically, yeah, we can do that. And these were the tasks we considered. And the tasks are simply learning the effect of the actions. Okay, so these are three different tasks, we say. And as you see, both have different property, and the system is collecting data and learning. So now the thing is which game the robot should play such that overall learning is improved. Okay. And the heuristic we tested here is learning progress. So learning progress means that which task is learning the fastest, meaning that if you have a learning curve which is reducing, for example, the slope of that learning curve is the key parameter. Okay? So if something is learned very well, you keep learning that one. But if you already stuck learning or you became perfect and you don't learn anymore, then you switch task. Okay, and we show that actually with this learning scheme, we could learn better compared to pure random learning with enabled connections, or with learning progress but no connections. So skill transfer and learning progress based task selection is helps learning to become better in all the tasks. And here on the right, I can show you how the tasks are selected. And you can see that there is some pattern. Each of them, each column is another trial, okay, with different random seeds and so on. You can see some pattern. I mean, there's some difficult based on the difficulty of the task. Some tasks are learned a little bit and then switch to other and so on. And this looks a good idea, but the current one is based on the learning progress. So what? Oops, can I go? All right. And now what we are working on, which is actually I didn't include the slides since this is going to be recorded. So now we are modifying this model to consider the neural cost. Okay, so you want to switch the tasks such that the learning progress and energy is somehow traded off. And with this one, we want to aim a good learning for all the tasks and also reduced neural cost, the neural energy consumption. Okay. And the result seems promising. Of course, if you just say pure energy means that you're completely lazy, you don't learn anything, you learn something and you're stuck with that. Well, it doesn't work. So you need to combine it with learning progress and energy. So maybe people's, let's say, laziness level is explained by trade-off between neural energy use and the learning progress. Okay, I'm sorry I took a long time, so I would like to basically just say I'm excited about interleaved learning, and I think it will connect us to neural economy, and that should be part of task arbitration. And right now, this energy idea is not much studied in machine learning, but I think time will come there. As an overall about this tissue stuff I mentioned, I mean, basically we need to understand how the brain does exaptation, I mean, the neural reuse and change of the used area, and synaptogenesis, which means that how the synapses, how the neurons form synapses that go and find their targets. Okay, so this needs some detailed modeling. And current machine learning approaches have to think about that if they want to be considered as models for brain computation. Okay. So with this, of course, I'm not against current AI. Okay. Mainline AI research will be around and will be very useful. But I think we have to understand AI in a way of, let's say, brain AI. Okay. So that's my goal. And I think I should stop here. And I don't know if I have enough time, but any questions I would like to have.